Also, let's talk about the week. We have kids on that we test convex real projected structures on reflection of. Yeah, thank you everyone who still survived. The, the, so I tried to explain the convex real projected structure on a reflection of epochs. This is joint work with Su Young Choi and Ludovic Marquis. So in fact, the idea of this story is quite simple. So I start from the polygon. So this is two-dimensional reflection of before. So the question will be so given this kind of like a combinatorial polygon, and then I give simply some labellings on the vertices. So it will be the dihedral angles. Okay? And the question will be how we can realize this the polygon as a hyperbolic polygon. Okay. Okay. So for example, so this is the pentagon. Okay. So I don't really want to always write the pi over 2. So I just write the 2. Okay. So please, you understand it's pi over 2 or pi over 5. So this is, I want to obtain this guy. Okay. So I want to understand, try to realize as a hyperbolic polygon, and then how many ways. So there are many ways to actually realize this polygon. So strategy is quite simple. So first, I think I consider this two triangles. Okay, so this guy is some ideal triangles, and then this is another, I mean the triangles of some vertices ideas, so hyperbolic triangles. Okay, and then you can actually deform it a little bit. So previously the vertex with ideal vertex, but some vertex now hyper ideal vertices, right? Okay. So then you can deform it, but then what you can do now, after deform it, you can actually make so this is a hyperideal vertex, and then you draw the tangent line, and then this line actually the perpendicular to this edge, and then this edge. This is a basic like a projective model of hyperbolic the space. But then now you can truncate. Okay, so now I think here, after truncated, the angle is right angles, right? But then you see, when the length is the same, those lengths of this edge are the same, then you can actually glue, right? So then, okay, the picture looks slightly different, but the idea is that basically you have a pentagon, and then you cut along the line, and then we have this two objects, but this is basically obtained from the triangles. Okay, so it's very similar to the hyperbolic surfaces. So you have a hyperbolic surface. So basic building block of a hyperbolic surface is parapents. Okay, so you understand the parapents, and then you glue this parapents. It's the same. So it's basically you understand the triangles, okay, and then you can glue, and then you understand that the hyperbolic structure on the polygon or the two-dimensional reflection of ripples. So this is ID, and then you can easily see that what will be the dimension of this deformation space or this Teichmann space for this guy. So here you see the length of this edge is 1 parameter, and then there are another length here, right? Okay. So in fact, the two dimensions of the space of hyperbolic structure on this reflection of ripples. Does it make sense? Okay. Then we want to generalize this kind of in this kind of thing is in higher dimensions. But as you know that if you have the compact one in higher dimension is by the most rigidity theorem is a rigid. But if you consider the convex projective structures, then there are sometimes some deformation. So But then we want to understand deformation space. So is there some questions? I think if you understand this one, then I think the remaining will be the fine. But of course, I want to be more precise. So, okay, so because this reflection will be false, so I think should start with some, yeah, the Cox matrix. So the Cox matrix is simply the symmetric S by S matrix with the entry is a 1, 2, and infinity, such that the diagonal entry is the 1, and then the off diagonal entry is the not equal to 1. Okay? And then whenever we have the Cox matrix, then we can easily produce this group, which is Cox group. And then the set of generator is simply this finite set S. And then the relations will be the ST to the MST. This is a relation. As you can see that because diagonal entry is 1, so every generator is involutions. Okay. And then of course, whenever MST is infinity, then there is no relation. Okay. That's conventions. So this is a Cox group. And then of course, this Cox group also you can encoded in some graph. It's a labeled graph. So people call the Cox diagram. And then the node of the set of the node or the set of the vertex of the graph is a labeled graph is the set S, sorry. And then the node are connected by the edge whenever this MST is bigger than 2. Okay. And then usually we put the labels on a edge. It's MST. Okay, so I will give the examples. Also, it's customary usually omit the label of the edge when the MST is 3. So I give the example. So this is one Cox matrix. So as you can see, the 1, 1, 1, 1, right? It's here. And then I put, okay, some 3 or some 2. Okay. Then the Cox group, okay, we have 4 generators. Okay, so S1, S2, S3, S4, right? And then this is relations. For example, because here M1, 3, so the 1, 3 entry is 2. That's why the S1, S3 to the 2, right? Here. This is a relation. And similarly, you put these relations. And then I want to encode this information or this information in this graph, is a labeled graph. Here, for example, like S1 and S3, this is place 2, right? So then I said there's no edge. Okay, 2 means there is no edge between. Okay? And then the 3, then for example, the 1, 2, and 3 is there are edge. And then of course I probably put the label 3 here, but as I said, this convention is label 3. Usually I omit the label. So this is the Cox diagram. In fact, this you can obtain from the reflection in the Euclidean space. So, okay. And the Cox group is irreducible if the diagram is connected. So previously, diagram is connected, so it's an irreducible Cox group. And then there's a well-known theorem by the Weinberg and Magrius is that every irreducible Cox group is spherical, affine, or the large. Here, the spherical means the Cox group is a finite Cox group, and affine means the Cox group is virtually abelian. Then the large means it has a finite index subgroup with the non-abelian free quotients, meaning that the free group of the rank bigger than equal to 2, right? Yeah, affine means is virtually abelian. So the group contains finite index subgroup, which is the abelian group. So in other words, in fact, the spherical means you can realize there's the sphere, I mean reflection in a sphere, and then the affine is basically the reflection in a Euclidean space, and the remaining are all large. But and actually the name is the Cox is coming from the spherical and affine Cox group is completely classified. So there are lists. So you can actually the check. And then, of course, we are interested in the large Cox group, which including for example, like a reflection group in a hyperbolic space, will be here, the large Cox group. Narrow spherical, narrow fine. Okay, so this is about the group I consider. And then I should talking about the reflection group in projective space. Okay, so my vector space is R to the D plus 1. And then we have this projective D spheres, which is simply the space of half line starting from origin. So it's simply double cover of projective space. And then the SL plus minus B is the group of projective automorphism of these projective spheres, which is simply the matrix group whose determinant is plus minus 1. Okay. And then we need to define reflections. Okay, so the reflections simply the order 2 elements which fix the projective hyperplanes point-wise. In other words, there exists a vector v and the linear function alpha, and my reflection sigma can be written as identity minus alpha tensor v with the alpha b is equal to 2. So alpha v will be the v minus alpha, sigma v is equal to the v minus alpha b times v. So for example, any vector in a corner of alpha is fixed points, right? And then if you put b, and then the sigma b will be the minus b, right? Is a reflection vector. So this is the reflections. Okay. Then okay, so I think we already probably know what is convex. Okay, so probably check. And then the projective, the polytope, because we consider this polygon or the polytope. So the special projective polytope is simply the properly convex subset P with a non-empty interior, such that we can write the polytope P as intersections of the half space, meaning that, okay, so here the alpha I is a non-zero linear functionals, and then the alpha I x is less than or equal to 0, and then all those is basically the half space, right? And then we of course the projective size, and then intersection of this half space is my polytope P. And then this is a common terminology. It's a face of the codimension 1. People call usually the facet. And then the codimension 2, people usually call the reach. Okay. So so dimension, for example, in a polygon, and dimension 2 for the polygon, the face will be the H, and then the reach will be the vertex. Right? Okay, so then now I think we want to produce some reflection groups. So I think we should start with the polytope. But as you imagine, the introduction that I introduced this polygon with the dihedral angle is pi over something. Okay, so basically that's I need for also the project setting. So the Cox polytope is a pair of the polytope P with the set of the facet. I think I write as a capital S, and then we have a reflections. Okay, and then of course each reflection sigma S should be related to the facet. Okay, so this is what I'm saying. So every facet, the supporting hyperplane of this facet S is simply the corner of alpha S. So this small s is a facet, and then this reflection is correspond to. Okay, so this is what I'm saying. And then the crucial condition is the second conditions. Every pair of the facet, I mean the different S and T, then okay, so the alpha S is a linear functional and BT is a vector, so this is a number, and this number, and then another number is kind of the opposite, so alpha T and DS. Those are the both 0 or the both negative, okay? And then this multiply these two number, this number should be bigger than or equal to 4 or equal to the 4 times the cosine square pi over MST. Here the MST is some natural number bigger than or equal to 2. Okay. Then whenever we have this polytope P, then we can produce the matrix AP, simply the S by S matrix. I call the Catalan matrix. So the AP ST is simply the alpha S BT. So whenever we have this polytope, then we can produce this matrix. Okay. So probably I try to explain what this condition means, the second conditions. Okay. So this is quite simple. So two different facets, S and T. Then we have the composition, sigma S and sigma T. So the composition of the two reflections. Okay. But there are this reflection, of course, act trivially on the intersection of the two corners. It's clear. So that in fact this induces the elements of the SLV quotient by U. So this is basically 2 by 2 matrix, right? And then this matrix will be conjugate to this kind of the hyperbolic matrix when this number is bigger than 4, and the number is equal to 4, and then it's conjugate to this like a parabolic elements. And then when the number is the 4 times cosine square pi over ms t, then it's exactly the kind of the rotations by 2 pi over ms t. So that's the conditions. So we need. So okay, and then because of that, I want to say that in the case C, okay, the last case, and then the dihedral angle of the ridge is pi over MST. Of course, I mean, in projective geometry, there is no angle, right? But at least in this case, I can define what is the angle for the composition of two reflections when this satisfies this. Okay, this makes sense. Okay, so then of course you can easily construct the reflection group. The Cox group. So the Cox polytope P, we can produce the Cox matrix. Simply the set of the facet is S. Okay, and then the pair of the distinct facet S and T. So the case C, in a case C, and simply the entry is MST, and then otherwise I just put the infinity, right? And then it gives us the group, Cox group. Okay. So the Cox polytope will produce Cox group, right? And then the relation between the reflection group will be the following: is by the Tits inverse. So the P is a Cox polytope with a Cox group WP. Okay. So I explained exactly how we can obtain from the polytope to this Cox group. And then this is abstract this group, but then we also consider the geometric group, which is gamma P, which is simply the reflection group generated by projective reflections. Okay. The fact is that the natural homomorphism from this Cox group WP to the gamma P by the generator, so the small s is a generator of this Cox group, right? This is mapped to the involutions, which is the sigma s, reflects the projective reflection, right? And then this homomorphism is in fact isomorphisms. So, and then the group, so basically the image of these homomorphisms will be the discrete subgroup. And then also the crucial fact will be the union of the gamma P translate of the P. So you take the translate and then take the union. Of course, this will be it will be actually some tiling of the power of the projective sphere. But in fact, important point is that this is the convex subset. So that's the link for the convex projective structures. So the convex subset CP, and then if you consider the interior, then this reflection group will act properly discontinuously on this interior. So what happens is that we have this nice convex domain, omega p, and then nice discrete subgroup, gamma p. If you take the quotient of omega p by the gamma p, then we have the convex projective orbifold. Okay, because it has a the torsion elements, right? So it's not the manifold, but it has orbifolds. So that's is a people usually call the reflection orbifolds. So singularity is the topological is a ball. It's a polyhedron, polytope, sorry. And then the singularity is a boundary, right? Is there some questions? Okay. So that's why I think, okay, the fancy terminology, I want to understand, for example, deformation space of the convex projective on reflection orbifolds. In other way, I want to understand simply that is some Coxer polytopes, okay? And then we want to fix some non-combinatorial polytope. That's I will explain soon. So that I think so first I think here the combinatorial polytope I want to explain, but it's quite simple. So the projective polytope P, then we have this phase poset, which is simply the order of phase partially ordered by inclusions. Okay. Then the polytope P and P prime a combinatorial equivalence if there exists bijections which preserve these inclusion relations. And then this is poset isomorphisms. And then combinatorial equivalent class I call the combinatorial polytope. So then the Label's polytope is a pair of combinatorial polytope with the Lich labeling on a polytope, which is a function of the set of Lich to the pi over m something. Okay, so it's if you're familiar with orbifold, then this is exactly the reflection orbifolds. I mean, this labeled polytope is a reflection orbifolds. You can consider it in that way. Okay. Lich is the face of codimension 2. So previously the polygon, the lich will be the vertex. At the vertex, we assign some the label. It will be the angle later, right? Okay. So some other questions? Yeah. So is yeah. Okay. So then of course I think we want to talk about the convex project structure on the orbifold. So that's exactly this one. So the Coxer polytope realizing labeled polytope is a pair of Coxer polytope P and then the poset isomorphisms such that the label of the Lich is Lich R of this labeled polytope is the dihedral angle of the Lich of P. Okay, so it's simply I try to realize this labeled polytope as a Coxer polytope, right? That's what I mean, right? But this is I just try to write a more formal definitions. Okay, then of course, then two convex projective structure are equivalent. It's basically the same thing as something like here. The two Coxer polytope realizing G are isomorphic. Then I mean there is some projective orthomorphism such that this orthomorphism map my P to P prime. And then, okay, this orthomorphism induce some poset isomorphism, then this should be I mean, this is natural, right? So then, of course, all collect those will be the deformation space of labeled polytope, which is the space of isomorphism class of projective Coxer D polytope realizing G, or simply the deformation space of convex projective structure on a reflection orbifolds of the same thing. And then notation will be the CG. Okay. So this is my target. And then I want to understand especially the specific examples, which is, of course, I want to understand in all the reflection of ovipoles or the labels Politope, but that's hard. So we will focus on the specific the Politope, and then I will explain what exactly mean irreducible, large, two perfect, and etc. But first, I think I want to explain the truncation Politope. So the polytope is truncation polytopes if it builds from the simplex by successfully truncating vertices. For example, like a D prism is a truncation D polytope obtained by truncating one vertex. So I give the examples. So this is a tetrahedron, is a simplex. And then if I truncate this vertex, then we obtain this one. It's prism. And then if I truncate this one, and then we obtain this one. Or I can also truncate this one, right? This vertex, and then we obtain this one. And then I truncate this one, then this one. So all those are the truncation polytope. So those are the polytope I'm interested in. The key fact is that you remember that the polygon case, any polygon is a truncation polytope, right? You start from the triangle, you cut the vertex. Okay, the 4 gone, cut the vertex, 5 gone, you keep going, 6 gone, yeah, right? So any polygon is a truncation polygon, right? But as you can see in the dimension higher than 2, yeah, that's not true, right? This is some specific the polyhedron, I mean the polytope, right? And in particular, uh, the truncation polytope should have the triangle, for example, right? Already you cut the vertex, right? The triangle should be. So for example, the cube is not the truncation polytope. Cube is not. Okay. But the key fact is the following. In fact, the truncation polytope can be decomposed into basically the simplices. That's why I try to consider this object. Then I think I want to understand the deformation space for the simplices, and then I want to glue. Then you can actually understand deformation space of those, I mean the labeled truncations polytope. So this is the idea. So that's why the introduction explains everything. So okay. Okay, so and then there was some more terminology. I need to explain the irreducible large. Large I already explained, but I should explain what is a large labeled polytope, and then the two perfect. So previously I explained when we have a Cox polytopes, then we can produce a Cox group. It's quite similar. When we have a labeled polytope, we can produce a Cox group, right? It's because the generating set will be the number, the zero, the facet, and then there are this angle, right? So okay, this is okay. Then I just simply say that the labeled polytope is irreducible, then corresponding Cox group is irreducible, and then etc. So spherical and then spherical or affine. So that's the terminology. Then for the two perfect, I need to introduce the link, and the link of the labeled polytope at the vertex is simply the link of the underlying combinatorial polytope together with the obvious rich labelings from this labeled polytope, right? Then the labeled polytope is perfect, meaning that the link is always spherical. So in other words, the reflection ovifold is closed ovifold. And then the labeled polytope is too perfect, meaning that the link should be the perfect. Okay. So I think you kind of understand why this. In fact, the terminology is coming from the paper of the Wimberg. So we just followed this terminology from the Wimberg, but the perfect is same thing as the closed ovifolds. Okay. Okay. So then I think I state the main theorems. The perfect means the link is a spherical, meaning that okay, so maybe I think so if you look at the vertex, okay, and then this vertex is contained in a okay this you just collect the facet contain this vertex. Okay, so that might be the in the dimension 3, might be there are 3 facet will contain this vertex, right? And then of course, I mean then you consider the subgroup of the Cox group, which is generated by the 3 phase, and then that Cox group is a finite Cox group and the sphericals. Then I call the perfect. So in other words, that the stabilizer of the every point in this is a orbifold. It's a finite. So it's a correspond to a closed orbifolds. Yeah, does it make sense? Yeah. Okay. So then let's state the Rawls main theorems. So the G is a irreducible large two perfect label truncation polytope of dimension d bigger than equal to 4. Then assume that the deformation space is non-empty. Then, in fact, there are upper bound for dimensions. So d should be less than or equal to 9, meaning that, okay, you can construct a lot of those labeled truncation polytope in higher dimension, but those does not admit projective structures. There is no Cox polytope realize such a labeled polytope when the dimension is bigger than 9. Okay, so here, whenever deformation space is non-empty, then the dimension has upper bound. So for example, yeah, there is no the Cox polytope which realize this labeled polytope in higher dimensions. Let's say, for example, 10. There's no such a, okay? So there is a limit. And then the deformation space is quite nice. It's simply the union of the finitely many open cell. And then we can explicitly compute the dimension is E plus G minus D, where the E plus G is simply you count the number of reach with the labels different from right angles. So you just you look at this dihedral angles, right? And this reach, and then the angle is different from the right angles, and then you count them. This is simply the E plus G, and then so E plus G minus D. Okay, so this is dimensions. Then another one is that if there is a hyperbolic Cox polytope realizing G, if and only if, in fact, the deformation space is connected. So it's, in other words, open cell. So you have this kind of reflection orbifolds, okay, which admits a hyperbolic structure. Then the deformation space is simply the open cell of dimension this one. Okay. Of course, in general, it can be some yeah, it's some several components, but whenever it admits hyperbolic structure or the hyperbolic Cox polytope realized in G, then the deformation space is connected. I just give 2 remarks. The first of all, the number of connected components can be explicitly computed. So if I have time, then I explain how to compute. And the second remark, but this labeled graph is not truncated a truncation polytope. Let's say the cube or some other cases. Then this deformation space may not be a union of open cell. So for example, there are the perfect labeled 4 polytope such that the deformation space is a circle, for example. Or there are some perfect labeled for polytope G2 such that the deformation space is homomorphic to the this shape, the cross shape. It's not anymore the manifold, right? It's this kind. So my point is that these conditions is crucial to obtain this the deformation space is a union of open cell. Uh, yeah, label polytope is a combinatorial polytope together with this labeling. So you can consider as a reflection of before. Okay. Yeah, is that's right. That's right. That's right. That's right. So and then the Cox polytope you can consider as uh, convex real project structure on OV4, right? Yeah, because Zoom. Yeah, yeah, that's right. Yeah, that's right. That's right. Yeah, that's right. So the labeled polytope is a combinatorial polytope together with simply the labeling. And then the Cox polytope is a geometric polytope which live in a projective space. That's right. This Cox polytope, it has the projective polytope together with these reflections. So uh, yeah, yeah, yeah. So of course, without reflections, yeah, we have this information of the reflections. Yeah, yeah, yeah. That's right. That's it. In hyperbolic setting is unique, but in the project setting, we need extra information, right? Not just the hyperplanes, which is fixed. Okay. So yeah, that's right. So it's uh, but if you have a uh, so the reason is that uh, is if you have for example like uh okay, so what I say is that so here we have this Cox polytope, and then which is we define as a I mean properly convex this set which is defined by this intersection of the blah blah blah. Okay, but then if we consider when this reflection group is a finite reflection group, it can be happen, right? But still the convex. But if you so so what I'm saying is that okay, uh, if you don't take this double cover, I mean the sphere, and then you do not consider the SL plus minus, simply the PGL, for example, then the previous map is not actually injective. I mean this can I go back? It might be this one. So here, the Tichy-Lindbergh theorem is for any Cox group. So it can be finite, for example, finite Cox group. Then in that case, for example, this CP or this omega P is everything for yeah. And then and then of course, I mean if we didn't take this one, then for example, this map we should if we change the like a PGL, for example, then this map some of the like involutions minus identity map is mapped to the identity, right? Yeah. So there are some small technicality, but other than that is it's okay, but it's not really big problems. Ah, yeah, that's right. That's right. So here, uh, so it's basically, I think, it's, so we want to show that the developing map is the convex, right? Yeah. Uh, yeah, I think, I don't know how I can, yeah, 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 yeah. Okay, okay. Yeah. No, no, no. I might be, yeah, might be I explain later, might be after. So, uh, yes. Oh, okay. So I think, yeah, I don't really have enough time, but it's okay. Yeah, so we are until here, right? So there are some counterexample when the labeled polytope is not a truncation polytope. Okay, so at least I want to explain how we obtain such a result. Okay, so let's go. So the first, I think, previously I defined kata matrix of the Cox of Polito, and then the kata matrix exactly satisfying such a properties. Okay, okay, and then the kata matrix, the reducible if the you can write is this kind of shape. So the A is a A1, like a block form, the A1 and A2. Then is a reducible kata matrix. And otherwise, I call the kata matrix A is irreducible. Okay. So as you can see here that the diagonal is 2, then the off diagonal should be the equal to 0 or the less than equal to 0, right? And then when we have an irreducible kata matrix A, then you consider the 2 times identity matrix minus A. That is all the entry is non-negative, right? So then we can use a Perron, thank you. Yeah, that's right. And then there are this simple eigenvalue, blah, blah, blah. And then we define A such the kata matrix is a positive type. This lambda is positive, and then the 0 type, then the lambda is 0, and the negative type, and then this lambda is negative. So yeah, let's look at this example. This is the simplest examples. The A 2, 2, okay, this is okay. Mu can be this range, or the mu is minus 2, or the mu is minus 2. But then, of course, the eigenvector corresponding to this Perron-Provence theorems, which is in this case simply the 1, 1 vectors. Okay, so the 1, 1 vector, and then of course when the mu is minus 2, then this 1, 1 eigenvector is eigenvalue 0. Okay, and then this is the negative, and this is a positive, right? That's right. So this is but then this is exactly the happen here. So in this case, okay. So the hyperbolic polytope is also the Cox polytope, okay. And then this edge will correspond to 1 reflections, and then this edge will be also correspond to 1 reflections. And then if you consider only these 2 reflections, and then it provide 2 by 2 solve kata matrix, right? So in this case, this is the ideal vertex. It happens exactly the mu is minus 2. And then if you deform it, then it's become hyper-ideal. Then this is exactly the mu is less than minus 2. It's a negative type. Okay, so this is the change of the, okay. So that's I explain. So whenever we define these reflections, then of course this is same thing as this pair, but this pair is actually the determined up to this simple actions, meaning that alpha s bs give a reflections, but lambda s alpha s and lambda s inverse bs also give the same reflections. It doesn't change, right? So that's why I think it's better to introduce this equivalence relation of kata matrices, which is the 2 kata matrices A and A prime are equivalent if there is positive diagonal matrix D, and then A prime is equal to D, A, D inverse, right? Because here the matrix, for example, the Cox polytope P will give us kata matrix, which will be simply the alpha S B T, right? But here the lambda S, so there are this lambda S. This will be exactly this diagonal matrix D, right? So my point is the Cox polytope will give the kata matrix, something like this, but this Qatar matrix depends on of course, the choice of the pair, but the equivalence class does not. Right? The equivalence class is simply the uh, aspect this equivalence class, right? And then the another crucial fact will be when we have this matrix A is irreducible, the negative type, and the rank is D plus 1, then there is Cox polytope such that the Qatar matrix polytope P is equal to the given Qatar matrix A. So in other words, actually the Qatar matrix encode all the informations of this polytope. So you can work in uh, the matrix. Okay. Then okay, so here the Label's polytope with the Cox group WS, and then let's say that this my Cox polytope P realizing this Label's polytope G with a Qatar matrix A. Then we look at this the K circuit, which is simply the K tuple of distinct elements. So here, for example, I1, I2, and IK. And then we can associate number. So using this Qatar matrix, simply the A, I1, I2, and A, I2, I3, and the A, IK, I1. But as you notice that it does not depends on this choice of representative, because here the one time I1, and then here another one time I1, right? So it will be the cancel out. So lambda S, for example, and then the 1 over lambda S, right? So this doesn't change. So this is the invariant for the equivalence class of the Catan matrix. So then, and then such a number we call the cyclic products. And then the thing is that, in fact, the Cox polytope are isomorphic if and only if the Catan matrix equivalence, if and only if the cyclic products are equal. So look at the cyclic products. That's enough. Okay. Might I think. Yeah. So I think it's probably I don't really have enough time, but at least I want to mention the following. And so as I said, so this is actually one truncation polytope, and then if I cut, for example, along this one, then we can decompose into these two. But as you can see here, this is simply you start with the tetrahedrons, and then some of the vertices will be truncated, then you obtain this one. It's like previously there's a pentagon, right? And then I decompose into the two triangles, and then some of the vertex of the triangle is truncated, and then we can glue, then we obtain everything. So it's a similar thing. So this is basically the tetrahedrons where the sum of the vertex is truncated. Also, this is the same thing. Also a tetrahedron, and then some of the vertex is truncated. So, but this guy is basically very similar to understand the deformation space of this guy is very similar to the understand of the deformation space of the tetrahedrons. So that's so maybe I think yeah. So I think it's probably I cannot really give the full descriptions, but yeah. Okay. So yeah. So yeah. No. I think it's probably I think yeah. So maybe I think I just give this case, and then might be so. I think I might just give the two lemma, which is might be essential, and then I stop. Okay, might be the 3 minutes. Okay, sorry. So the key thing is that truncation polytope you can decompose into basically the simplest with some of the vertex is truncated. Okay. So then first I want to understand deformation space of the simplex. Okay. Then if you look at the the this the Cox diagram of the Cox group of this labeled simplex S. So this is in fact in the dimension d bigger than or equal to 4, there are four type, tree, or the cycle, or the pen, or the K23 types. Okay, this kind of type. And so the other case is quite simple, so I explained these cases. So in fact, so A25, A54, A43, A32. So this is the one cyclic products, right? Okay. And then so this one is the opposite directions. So 25, 54, 43, 32, and then this is 25, 54, 43, 32. So one cyclic products has actually the same information as the ratio. The reason is that if you multiply this cyclic products together with this one, it is fixed because A25, A52 is a 4 times cosine square pi of something. It's fixed. So my point is that this ratio, I mean, this information of the ratio is the same thing as simply the cyclic product. This one. Okay. So this is one variables. Okay. So this is corresponding to the this one 2, 5, 4, 3. Okay, so this one, and then the another one is the 1, 4, 4, 5, 5, 2, 2, 1. So this one. Okay, so this is another variable, and then you can also see the this cycles, right? And then the 1, 2, 2, 3, and 3, 4, and 4, 1, right? Those are the basically the only cycles which is non-zero, because let's say the cycle A35, there's no edge, it's right angle. So this is a zero, right? A35 is zero, right? So those are the variable, but point is that, so this is X variable, this is Y variable, and this is Z variable, but it has relations. This simple relations. And then this is zero. So you can see it's basically, you simply look at uh, uh, the this guy, and then how many circles, and then of course this is a two circle is essential, and then remaining are just it's obtained by I mean take the log and then plus, right? So for example, so here uh, when the simplex has like a this diagram is something like this, then the this dimension will be the 2. This dimension is 2 because E plus is simply the 1, 2, 3, 4, 5, 6, right? 6. And then this is actually the D is dimension 4. So this is a 2. And then similarly, this is just dimension 1, and also this is dimension 1. Yeah. And then the last one, I think I want to mention is that, yeah, it's no. Okay, so maybe I should stop here. So my point is that try to understand the simplex. We simply understand this the relation between the cyclic products, and then the cyclic product is the variables, right? Is give us the parameterization of the deformation space for the simplex. Okay, and then as you can see, it's quite simple. And then later to glue, you use, for example, like whenever you wanted to glue something, and then this kind of the variable should match up. And then whenever match, then there are actually some bending. And then you count all these deformations, and then you can actually compute. So this happens also the simplex, but this same dimension count is also for the general truncation polytopes. Okay. I think I should stop here. Sorry. Yeah. Sorry. All right, please. Thank you. Yeah. So here you simply take the uh, K tuple of the distinct elements. So the I1, I2, let's say IK. So the K tuple. So okay, or there might be the yeah. You can say might be S. Okay, might be like there to SI1. It's too many indices. So might be the SI1, uh, SIK, right? Then we can define this number CA, which is the yeah, in this way. So A I1, I2, and A I2, I3, and etc. And then, as I said, it's A Ij is simply the alpha I and B. It was V, right? It's a Bj. But then the whenever you get the sum invariance, should be those should be non-zero, right? The zero is nothing, right? So that's why the yeah. So here we only have we should only consider this three cycles. So this guy or this guy or this guy, because when if you something is like A15 or the A35, this is zero, right? What I'm saying is okay. So if I take the uh, in this case S, let's say 1, S, let's say 3, S5, for example, then this is A, S1, S3. But what is that? Exactly. So the A, S1, S3, there is no edge. So, I mean, this is the label 2, right? So this is 0, right? Yeah. So we should look at the cycle and this loop, which which is yeah in this diagram, right? That will give us the parameters for the deformation space. And then what I'm saying is that uh, there are three such uh, this one and this one and this one, but of course obviously there are relations. I mean this is quite clear, right? Then it's essential the parameter is two parameters, right? So this one cyclic products and this cyclic products, because whenever this cyclic product is determined, then the other one is also determined, because this one and this one, if you multiply, then it's fixed, because the A25, A52 is the 4 times cosine square pi or something, already fixed. So my point is that this ratio exactly the same information as just one cyclic product, this one. Okay, and then there are three kinds, but in fact there are obvious. I mean, if you draw this one, and then the outside, I mean, it should be the relation, right? So three variables, but the one relations, and then so it's a easy relation. It's a two parameter space. Yeah, it's R2, right? So this is X, and this is Y, and this is Z. X plus Y plus Z is 0. So we have a two parameter space. So my point is that that's why it's quite easy to compute the deformation space of the simplex and the label the simplex, and then the truncation polytope you can obtain from such several simplex, and then you truncate some of the vertex, and then you glue them. Yeah, so that you can actually do the exactly same thing as the like a polygon. Yeah, triangle, and then yeah, you glue them. Yeah.